All right, 8-6 in Advanced Algebra 2, doing some log story problems, or kind of log story problems. We're going to do it a deal way. That's a problem-solving process. Define what you know with variables, write an equation, act it out, and label your answer in a complete sentence. And it's kind of the whole point of what logarithms are, to handle some of these story problems. So let's dive in. Some of these will move pretty fast, so if you need to pause the video, please do so. So here we go. In 2015, the world population was around this many billion people. Then in 2020, it was this many billion. Find the rate of growth for the world's population, round to the nearest hundredth of a percent. So check it out. We have to decide what formula we're going to use. And here's a bunch of formulas we did this chapter and last chapter. And population growth, it doesn't say that it happens continuously, but we have to realize that population growth happens continuously, so we're going to use a PERT situation. So the first thing we'll do is we'll label these steps D, E, A, and L. So this is our D step. This is defining our equation in our variable, so we're going to use this formula, amount equals PERT. And then what we'll do is every variable involved, there's an A, there's a P, there's an R, there's a T. We're going to write them out also. Remember, E is not a variable, E is a number. And we're going to go back through the story and figure out which of these we know and which one we don't know. We shouldn't know one of them. It's the one they're asking us to find for a question. So when they say find the rate of growth, that means we won't know R. That's our growth rate in that situation. So we should know everybody else. So A is the amount when we're like all done. And in this time scenario, since 2020 comes after 2015, the world population in 2020, the 7.794, is what will be our final amount, because that's the later in time. That means the principal amount when we started studying this stuff was 7.379. And yes, they are in billions, but we'll use these numbers. The rate we don't know, so we'll just put a blank there. And the time, since it went from 2015 to 2020, is 5 years. So this is really worth kind of the most amount of points in these problems, is all of the defining, the D step. E, then let's substitute all this stuff into this equation. So we can just put all that stuff in. Again, this is where we're going to move kind of fast to solve for things. And we'll notice once we've solved this, or excuse me, once we've subbed this stuff in, the variable we're looking for up in the exponent. This is the whole purpose of logarithms, right? How can we solve for a variable when it's up in the exponent? Well, the first thing we really have to do before we can start using the logarithms is get the base all by itself, e to the whatever by itself. There's a times 7.379, so we'll divide by 7.739. And you know what? You can punch it in your calculator if you want to, but it's going to come out nasty. So I don't want to punch it in my calculator. I'm just going to leave it like this as a fraction. And now that you've got the base by itself, we can get this exponent, which I called 5r right away, down in front by logging both sides. And you get a choice. Should you use the common log log, or should you use the natural log? Well, since e is the base, it would be much better for us if we use the natural log. So by natural logging both sides, we'll natural log this side. And I'm just going to leave it like that. But remember, Mr. Exponent comes down in front when you do that. So you'll get 5r times the natural log of e. And this is why we wanted to use the natural log, because the natural log of e is really 1. It's saying e to what power is e? Well, that's 1. So this you can just kind of scratch out because it's like 5r times 1. So beautiful. And now, remember, the goal is to just solve for r. So there's a times 5 hanging out with it. So we will divide by 5. And now for the toughest part, is to just punch this guy into our calculator. So what I'll do is I'll figure out this numerator, the natural log. Remember, that button is right here. And it starts the parenthesis for us of 7.794 divided by the 7.379. Close that guy up. I'm just going to hit equals after this. So I get this nasty number, and that's got to be divided by 5. So, and it's really weird. It's like, holy cow, look at this tiny, tiny number. Well, yeah, because we're solving for a rate. So we will round that off to, I put about 5 decimal places there. R was about 0.01094, but remember they wanted us to round to the nearest hundredth of a percent, so that's 2 decimal places. But you got to move this decimal 2 places in the first place just to turn it into a percent. Then you want 2 spots after that. So that's why I'm calling that about 1.09%. The population growth happened at about 1.09%, which is small. It should be small. And then the very last thing is L, label your answer in a complete sentence. So the growth rate is about 1.09%. Has to start with a capital letter, has to end with a period. This is worth 3 points all by itself. 1 for a capital letter, 1 for a period, and 1 for actually writing the sentence. No abbreviations either. And that's so we defined what we needed. We wrote an equation. A is act out your equation by solving, so that's all the work. And then finally, label your answer in a complete sentence. Let's move on to Yolanda. Yolanda's grandma left her some money. Thank you, Grandma. Yolanda put that money, which was $6,500, into an account that earned 5.8% interest compounded monthly. Bing, bing, bing. How long will it take for that money to triple, round to the nearest tenth of a year? So compounded monthly is the most important part because that gives us our equation that we're going to start with. It is not continuous, it is the compound interest formula, which is right here. So we'll start by defining the formula that we're going to use and putting all of the letters involved with that guy. So if you need to pause to write this out, feel free to do that. I just took a sip of coffee, so maybe you didn't need to pause. And then we'll go define things. Here's kind of what I do, is I go back to ask the question. They say, how long will it take? That's what they're asking me, how long. So that's time. That's the one thing we won't know. Every other variable, the A, the P, the R, and the N, we should be given up here in this problem. And they kind of trick us because they don't tell us the amount that we'll have when we're all done, because this is the principal. This $6,500 is totally the principal, but they say Yolanda's money is supposed to triple. So what you got to do is take the $6,500 and triple it, and that's the amount that we'll get when we're all said and done, which is the $19,500. And the rate, they told us, we just changed it to a decimal. And remember, N stands for number of times compounded, so monthly means 12. And time, we don't know, so we'll put a blank there. So trying to just save a little time, I just hit the old next button because I had it all prepared. And then we'll take this info and substitute it into the equation. And then this is what we want to do next, is act this guy out and solve for t. Notice where t is up in the exponent. It's time for logarithms. Before we can start logging both sides to bring this guy down to Chinatown, though, we need to get the base all by itself. And the base is this pink box, because the base is really this orangey McOrangerton nugget, which is going to be nasty McNasterton, so we're just going to leave him like this. So before I can log both sides, I got to get this 6,500 over to the other side. Since it's being multiplied, we will divide both sides by 6,500, and bada boom, look what number we came up with, a 3. Because that's what they wanted to happen. They wanted this money to triple. That's how we got this 19,500 in the first place. So divide that principal over, get a 3, or whatever number it turns out to be. In this case, it's 3. And now it's time to log both sides. You could LOG both sides, or you could natural log both sides. The only time I would natural log both sides is if the base was E. And see him? He's not E, so I'm going to common log both sides. I'm going to whoa, brother, hit that a little too fast. I'm going to common log both sides, and that brings Mr. Exponent down in front. So I got the log of 3 equals all of this mumbo jumbo. And what we have to kind of learn, this is one of the tougher ones, is this, if I can get my pen back, was what I was trying to do, this stuff in parentheses, we just have to treat it like you take a blind eye to it, like you really can't see it. And if you look, you just got one term over here, and you just got one term over here. All of this stuff is being multiplied together. So if we're trying to solve for t, and all this stuff is being multiplied together, it's like, what if I just totally rearrange this t into 12? You know, it's like if the t was all of this stuff is being multiplied together. To get t by itself, you just divide by all that stuff. So t equals, here's that log of 3, and we're going to divide it by the 12 is down low, and so is the log of this whole argument. So all of that we'll write out. It takes a little while to write that out, so if you want to pause, that's great. When you get it written out, we'll punch it in. That is the most complicated thing also, to punch this in. Before I punch it in, I would like to kind of use common sense and guess. How long should it take for somebody's money to triple? Well, we're getting a pretty darn good interest rate right here. And it should probably take, you know, it's not going to happen tomorrow. It should take quite a few years for your money to triple. Maybe like, you know, 20, 30 years, something like that. So that's just a rough estimate. It shouldn't take 100 years or anything like that. It definitely shouldn't take 1,000 years. We don't even live that long. So to punch in, here's how we're going to punch. We're going to do just like we normally do. Let's get this whole denominator. At first, figuring this weird number out. So I'm going to do the 0.058. Let me just clear everything out here. 0.058 divided by 12 and hit equals. And see, like, that's a nasty number that, you know, we would normally round off. We don't want to round that off. All we want to do next is add 1 to it, because that's what would happen. So I got this nugget in here figured out. Then I need to log that number. So I'm going to log it. So log of my previous answer. So I got that. So I got all this orange stuff right here. But you notice I still got to take that dude times 12, because there's a times 12 in the denominator. So times 12. Boom. And I got the whole denominator, so now I need to do the log of 3 divided by that. So just got to watch if I can bring my calculator back. Get ready. Log of 3, but you got to close that parenthesis up. That's the biggest mistake. Log of 3, close it, divided by a previous answer. So boom, and there we go. There's a number that seems to make some pretty decent sense. You know, it's like I said, it should take about 20, 30 years for this money to triple, depending on your interest rate. So I got it all solved. They say round to the nearest tenth of a year, so that's going to round to 19.0. I know it's weird to put the 0.0, but that's what they told us to put. So t is about 19.0, and then we'll label our answer in a complete sentence. Need a capital letter, need a period. It should take about 19.0 years for Yolanda's money to triple. I know it would be very easy to want to just say 19 years, but they said round to the nearest tenth, so that's what it did. So cool. All right, keep on keeping on. Carbon-14 dating. There's a nice paragraph on your worksheet that tells you what carbon-14 dating is about. It's about how scientists measure how old stuff is. So if you're interested, read that juicy problem. It's pretty cool, you know. But carbon-14 dating, they can tell how old things are. So it says use this formula. So nice. We don't even have to figure out a formula. They just say use this formula, where A stands for the initial amount of carbon-14. That's kind of like your principal. And T is the number of years ago the animal lived. And Y is the remaining amount of carbon-14 after it's lived 2 years. So let's kind of do that. We'll write our formula down. Let's define what we know. We know our formula, and the variables in it are Y, A, and T. Then it gets a little bit confusing after that. The easy way to figure out something of what variables you are given is to go see what the question is asking. They're saying, how old is it? Well, if they're asking me how old it is, that means I won't know time. So time is what's missing. Then we have to go figure out, like, the A, which is the initial amount of carbon-14 this guy has, and Y, the current amount of carbon-14, like when the scientist picked it up out of the ground and stuff. So the initial amount of carbon-14 is so easy that it's hard. The initial amount of carbon-14 that this organism had when it was living is 100%. They're talking about the percent of, like, carbon-14 it has, so it had 100%. But we don't want to put 100 in here. We want to put 1, because 100%, if you change it to a decimal, you know how you move it 2 places, is really the number 1. So that's so easy that it's challenging. It's like, oh, it started with 100% of its carbon-14. And then the other tricky part about this guy is, oh my, he has lost 95% of its carbon-14. We don't care about how much it's lost. We care about how much it's kept. So if it's lost 95%, it has kept 5%, which we need to change to a decimal. So that's interesting and challenging right there. If you lose 95%, you've kept 5%, so that's all we care about here. And again, the initial amount was 100%, and we don't know the time. So if you see problems like that on the homework, please refer back to this for an example. They're not exactly like this, but they're close. So, all right. Then let's substitute that in to write an equation. The A amount was, the Y amount was 0.05. The A was 1, which I didn't even write it down, and it was e to this nasty McNasterton little exponent. They want us to solve for t. T's up in the exponent. That's where logs come in. And because e is the base, we're going to natural log both sides. Why do we do that? Because the exponent comes down in front when you have logarithms. So natural log of 0.05 equals exponent, which came down in front, times the natural log of e, and that's why that's beautiful, because the natural log of e is really 1. So we can just scratch him out. And to solve for t, baby, there's a times negative nasty, so we're going to divide both sides by negative nasty. So natural log of 0.05, boom, boom. Make sure you close up the parentheses. It's clear so you can see a little better. Clear. Natural log of 0.05, close it, divided by nasty town, negative 0.123112. And how long should it take? You know, this is a fossil underneath the ground, and it's lost 95% of its carbon-14, so it should be there for a very, very long time. Yes, 24,000, almost 25,000 years old. You know, expect a big number like that when it's really, really old. How do I know it was really, really old? Because it's lost a lot of its carbon. You know, the more you lose, the older you're going to get. So then we'll label that in a complete sentence, and let's see how they told us to round. I just rounded to the nearest whole number. On quizzes and tests, we'll definitely tell you how to round, so don't worry about that. But I used my common sense on rounding. This is the decimal my calculator showed up with, but you know what? We're just going to call it about 24,964 years old. So good question there. Just a couple more. At the end of an advertising campaign, the daily sales of a product fell rapidly. Here's what an advertising campaign is. It's like if a new iPhone is about to come out, they're going to say, hey, coming August 1st, iPhone 17, you know, coming out. Get your orders ready. iPhone's coming out August 1st. iPhone's coming out August 1st. They're advertising for this to come out. So that's an advertising campaign. And at the end of it, it comes to a point where they don't need to advertise for it anymore. You know, it's like, okay, it's August 1st, the iPhone's coming out, and then, you know, in August, they'll still advertise, like, hey, instead of saying it's coming August 1st, say, hey, now available, go buy the iPhone, go buy the iPhone. But it gets to a point where they don't need to advertise anymore. Everybody knows that this iPhone came out, so they end the campaign. Bing! At the end of an advertising campaign, here's what the equation looks like for sales. The sales looks like this. And it's not an iPhone, I'll just use that for an example. But notice this is a decay because the exponent is negative. You got a base bigger than 1, e is like 2 point something, and the exponent is negative, so this is a decay situation. It says, what were the daily sales when the campaign ended? This part is not a deal problem, so they're just asking us the question. So when the campaign ended, that means if x is the number of days since the end of campaign, that x equals 0. So if we put 0 in for x, tell you what, I could do that without a calculator. Like if I put 0 in for x, this is 0. E to the 0 is 1. And 1 times 3,200 is $3,200. So they made $3,200 of sales the day they decided to end the campaign. Let's pretend that was September 1st. You know, it's like, oh, September 1st, no more advertising for the iPhone that's coming out. Well, they still made money that day in sales. People were still buying it. They're just not putting ads on the radio or on the internet or wherever. So they're still going to make money on that dude. And then that money is going to go down as the days pass because they're no longer advertising, and a lot of people have kind of already bought it if they wanted it. So how many days have passed after the campaign and before the sales were below half? So let's deal this guy. To deal it, we start with the equation. They gave that to us, so nice. We'll define our equation and the variables involved with it. We'll throw that, there's only two variables, an x and an s, all right? So we just got to figure out what they're asking us. How many days? Well, that's x. X is the number of days, so x is what we don't know. That means we should know s. They say the sales should be below half. We're going to actually set it equal to half and then kind of approach the problem that way. So if they had $3,200 worth of sales this day, then half of that is $1,600. So we'll sub all that good stuff in to the equation. And notice, meow, 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 we've got a variable up in the exponent, so we'll need to log both sides. But before we can log both sides, we've got to get this base all by itself. So we'll divide the 3,200 over since it's being multiplied. And, of course, bing, we get 1/2. That's what they wanted to know, when half of the sales were there. So it turned out to be 1/2. And then to do this, we will log both sides. And the log that I will choose is the natural log because e is the base. Why are we logging both sides? So the exponent can come down in front. And then after that, it's a simple move because the natural log of e is 1 right here, so it scratches out. Divide by negative 0.08. Natural log of 1/2, put that in parentheses and close it up, divided by negative 0.08. Punch it in, and let's see how many days it took. 8.66 meow, 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 meow is what I get. If you need help punching that in, let us know. But that means that happened on the 9th day. Like 8.0 is 8 full days, so then you start the 9th day after like that. So it took 9 days. On the 9th day, it took for the sales to dip below half. Cool. So far, logs have come in really helpful when we're trying to solve a real life situation. Let's check this one. Period of constant inflation. The value of a $100,000 property increases. Inflation means it's going to go up. So by 3% is what this is saying. You got a 3% inflation rate. It's constant, so that's why there's an E involved. And this was the principal amount. In how many years will the value of this building double its current value? So we'll define. They gave me the formula, and you need to double the value. So the value is going to be $200,000. And they want to know how long that will take. So I will let you pause the video, substitute this stuff in, and solve for t using logarithms. So give the video a pause. Let's see how we did. Sub it in. Got to divide by the 100,000 first to get the base all by itself. So there's your double. And to bring the exponent down to Chinatown, we're going to natural log both sides because e is the base. And to solve for t, there's a times 0.03 in front of it, so we will divide. Just make sure you close up those parentheses when you type the natural log of 2. And it took about 23 years, a little more than 23 years. 23.1 is what my calculator kind of came out with. So we'll label that in a complete sentence. It'll take a little more than 23 years or about 23 years, however you want to say it, for the building to double in value. And then I think we got one last one. This one's different. So it's easier than you think, but it's different. Steve predicts that he will need $80,000 for his new daughter's college fund. So he's just kind of guessing into the future here. Steve found a bank offering this much continuous interest. How much money does he need to invest now for his daughter to have this $80,000 in 18 years? This is a very common question that people go to financial planners. It's like, how much do I need to invest right now so I can have this much in the future? So because it's continuous interest, we're going to roll with some PERT. So we'll define that. We got the amount equals PERT, and we'll fill these things out. They want to know, how much should you invest now? Well, that is the principal. And that's what we don't know. So this is the one thing that's missing, is the principal. We do know the amount that he wants later. That's your 80 grand. We do know the rate, it's 0.048, and we know the time is supposed to be 18. So the one thing you don't know is the principal in this case. So let's go ahead and substitute this into our formula. The 80,000 goes over here for our amount, and P is what we don't know, and we got all this. I'm going to clean that mess up, though, by taking 0.048 times 18. And if you punch that in, you get 0.864. So you got e to the 0.864 if my pen would work. And to solve for p, you know, we don't need logarithms at all in this problem because the variable is not up in the exponent. He's down on the normal level. So to get p all by itself, there's just a times e to this number. We're going to divide both sides by e. So 80,000 divided by e to this, and we'll punch that in. 80,000 divided by e to the e to the already puts the exponent thing for you, so you just put the 0.864. And this is how much money that Steve should invest normally. So I will round that up a little bit to 83 cents in that case, because if you put 82 cents away, like, it really wouldn't add up to be the 80,000. So always round up a penny. It's similar to those loan problems. So Steve should invest $33,717.83 at this time. Now, a normal person would see this amount. This is what the financial planner comes back with, and they'd probably just round that to, like, oh, so I'll do like $33,800 or whatever. Some people might even go up to $35,000. But this is the minimum amount that he needs to invest now for this scenario to work out for him. So, all right, man. Good story problems. Last unit of the chapter. Let us know if you have any questions. Have a good one.